Hi and welcome to MSc. In this video we're going to look at isotopes. So what is an isotope? Well, to understand an isotope we have to remember a few things about atoms. So the first thing we have to remember is that it is the number of protons that defines which element the atom is. So for example, if an atom has 6 protons, then we know it has to be a carbon atom. So if we look here, here's a snapshot of periodic table from the IB data booklet. We can see that carbon is element 6. So that 6 there tells you that carbon always has 6 protons. That's how this is organized. So carbon's atomic number is 6, and that means any nucleus that has 6 protons will be a carbon nucleus. We also have to remember, of course, that protons and neutrons are in the nucleus of atoms. That's what makes up the nucleus of an atom, and the electrons are found outside the nucleus. So any nucleus, as I said, that has 6 protons in the nucleus, regardless of how many neutrons, is a carbon atom. And so what an isotope is, if we have atoms with the same number of protons but different number of neutrons, then they're isotopes of one another. So it turns out that the number of neutrons can vary. So how can an atom of an element exist with different numbers of neutrons? Well, remember, because it's the protons that distinguishes the element, we can have different number of neutrons. So neutrons are very much like the glue that hold the nucleus together. We have to remember that protons, because they're positively charged particles, they repel each other. They repel each other through the electrostatic force, right, which is a piece of the electromagnetic force. And this positive and positive charge relationship between protons causes a repulsion. It is a long-range force, which means particles and protons on either side of the nucleus and all throughout all want to repel one another. So it doesn't really make sense that all these positive protons will all hang out together in the nucleus. Neutrons, though, they don't feel any electrostatic force because they're neutral. So they don't feel any of that repulsion. However, both protons and neutrons feel the strong nuclear force. And this is an attractive force for the most part. If they get too close, it does repel them and kind of keeps a stable shape of nucleus. But it is an attractive force. It is, however, a short-range force. So what this means is that the neutrons need to be scattered throughout the nucleus, acting as these short-range attractive forces that help offset the repulsive long-range electrostatic force that the positive protons feel. So neutrons are like this glue that hold the nucleus together. So does the number of neutrons affect the nucleus of an atom? Well, sure. If I have too many or not enough neutrons, the nucleus can break apart. And we call that decay or radioactive decay. And in fact, isotopes that will do this we call radioisotopes. I always think about it, if I don't have enough glue in the nucleus, the protons are going to repel and break apart. And in fact, if I have too much glue, if you've ever done a craft, for example, and had too much glue in the craft, it doesn't hold together properly. It's kind of the same idea here, if you like that analogy. The other thing that different number of neutrons can affect is the mass of the atom itself, because of course we're adding neutrons to the nucleus. And this can have different effects in terms of how it behaves and its density. We use, for example, in Canada, we use heavy water in our nuclear reactors because it slows the neutrons down a little bit more, and heavy water uses a heavier than normal isotope of hydrogen. So is there a notation that we use that indicates the specific isotope? And of course there needs to be, because in some processes we need to know exactly which isotope we're talking about. So hyphen notation indicates the mass number of the isotope. So we have to remember what mass number is. Mass number is the sum of the number of protons and neutrons. So really it's the mass of the nucleus based on a relative scale where both protons and neutrons have a relative mass of 1. This is sometimes called the nucleon number, right? The particles that live in the nucleus. So here's an example for us to look at, and you might have seen this hyphen notation before, and it's indicating the mass number. So both this 12 and 14 indicate the mass number here. Alternate forms here would be something like standard atomic notation, or sometimes called nuclear notation, or nucleon notation, where for the carbon 12, for example, you might have seen it written as a carbon, and then a 6, and a 12. And what that tells me is the atomic number is 6 protons. Well, we know that because carbon is element number 6. Carbon always has to have 6 protons. And then it has a mass of 12. Well, so what this does, this notation here, is it says, look, we always know carbon has to have a 6. So why write it like this? We can just refer to it as carbon 12, or we could refer to it as carbon 14. And so rather than writing subscripts and superscripts like standard atomic notation would require, or nuclear notation would require, we can write it with this hyphen. So what this tells me, of course, is that carbon 12 has 6 protons, so the number of protons equals 6. And of course, over here, the number of protons also equals 6, because carbon always has 6 protons. So we can also solve for the number of neutrons in both of these isotopes. Because we have this formula here for mass number, which is what this part here refers to, the 14 and the 12, refer to the mass number. So I can then solve for the number of neutrons by rearranging. And I can say the number of neutrons equals the mass number subtract the number of protons. And of course, I know the number of protons because I can look it up in the periodic table if I don't already know that carbon is number 6. And so here I would say, okay, well, in carbon 12, it would be 12 because of the 12 here minus the 6 because of the proton number, which would tell me I have 6 neutrons in this isotope of carbon. In this other isotope of carbon, which carbon 14, it would then have 14 because of the mass minus the 6, and this would have 8 neutrons. Okay, as it does turn out, carbon 12 is the most common isotope of carbon that exists naturally. And if we look at the periodic table, we can see that the number underneath is close to 12. So typically, if we round the number under the element symbol, we'll get the most common isotope. That generally works. The number underneath is what's called a weighted average, where it averages all the isotopes that exist naturally and is weighted based on how prevalent they are, right? What percentage of carbon atoms have these different number of neutrons. That's why we have decimal values underneath. And we can see here that carbon 12 is quite likely the most common isotope, and certainly it is. Here we have carbon 14, which is a different isotope. It's still carbon. It has 8 neutrons, and it turns out that this one is radioactive, and it's actually the isotope that we use for carbon dating when we try to age items based on how much carbon 14 it has. The key takeaway for an isotope is that it's not fair to say that this is the atom, even though it's the most common one, and this is the isotope. They are both isotopes of each other. The most common isotope for this case is carbon 12. Hyphen notation avoids us having to write the atomic number, and it's a bit of a cleaner notation that way and avoids the subscripts and superscripts. I hope this brief run-through of isotopes has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you so much for listening and watching.